All right. Nothing worse than computers running your life. They put this new control box over here, and it's always doing something one doesn't want it to do. So, okay. So we were talking about networking last time, and everybody can close their laptops. Plenty of time to work on Project 2 if you're, or Project 3 if you're still doing that. So if you remember last time, we were talking about point-to-point networks, and there was some terminology that we threw out, and I just wanted to make sure that it was there. So the key thing about a point-to-point network is it's only one item on either side of a wire. Okay, so that's the point-to-point notion. And the reason point-to-point is faster than broadcast, does anybody have any good reasons for that? I mentioned a couple last time. Go ahead. Capacitance, you know, if you're connecting to a bunch of things, there's a lot of capacitance that you're yanking around. What else? Anybody here a hard EE type that might know another reason? Yeah. Yeah, what about impedance? Good memory. So the issue, if you have a multi-drop communication, is you can get reflections unless you're really careful at your impedance matching, and it turns out that you can't send things quite as fast either. And so it's much harder to tune a multi-drop thing than it is a point-to-point thing. So both capacitance and impedance matching basically mean you can run this sucker much faster. All right? And so that's kind of cool. And then coupled with the fact that because this switch is in theory smart enough to route single conversations across it, then you can have many more conversations going on simultaneously than if we replace this switch with, say, a hub. Okay, so I talked about a switch versus a hub. A switch is an intelligent wire-like replacement that attempts to figure out what conversations are going on and route them point to point kind of through the switch. A hub is kind of like a intelligent wire still, but it's not as intelligent. So if you send a message through this port in a hub, it actually broadcasts everybody connected to the hub. Now, it used to be that hubs were what you bought because they were much cheaper, but pretty much nobody buys hubs anymore. It may be that you get a hub if you buy a really low-end router or firewall, but pretty much nobody buys hubs anymore. And then, of course, we talked about the difference with a router, and a router is something that knows a bit higher level protocol than just the lowest level. So this is routing Ethernet MAC addresses around, whereas a router is more intelligent. It's possibly routing IP packets. Okay. Were there any questions on these pieces? Okay. So at the very end, we started talking about subnets, and the notion of a subnet is basically a set of things connected together, and the destination addresses are typically related in some way. And in particular, I talked about with IP, both v6 and v4, the notion of a subnet is pretty much coincident with this notion of a mask. And so here we have 24, since 32-bit IP addresses, we have 24 ones and 8 zeros, also represented by the number 24. This is the set of bits in an address that match if you're in the same subnet. So how many items can be in the subnet? Well, no more than 8 bits worth. And it turns out, actually, when you you use 0000 is typically not used, and 1111 is typically your broadcast address, then probably only have 254 items in here in this particular subnet. Okay? And then, so in the case of IPv4, it's identified by a 32-bit value. So here is an example, 128.32.131.0/24 is basically a subnet that all of the machines on that subnet start out with 128.32.131, and it's really that last digit that varies. Okay, and you can write either in the /24 notation or the mask notation. Both of those are equivalent. Okay, and then what's the difference between a subnet and sort of the whole address range? Well, typically subnet is, first of all, a subset, and secondly, it used to be that a subnet was kind of a physical wire. And so when I mentioned the idea of there being coax cable running in the roof that then came down, drops. Those were all the same subnet, and that was kind of the standard thing. Now a subnet's a little dicier. It's not clear that that notion's there because we've got switches, but a subnet is kind of a routable destination. So typically the routing process tries to get eventually to match all the bits in the subnet so that you can get to that subnet, and then the switches kind of take over from there. Yeah.
Does the 0/24 mean that you only get 24 unique IP addresses?
No. So /24 and 255, 255, 255.0 are the same thing. So it really means that the subnet has to match the first 24 bits, and then the rest of the bits, which there are only 8 left, are the subnet piece.
So why did they decide to put IP addresses in decimal blocks?
Why decimal blocks? I don't know. Why not? I mean, I guess, it'd be nicer to have hex, I suppose. And actually, when you get to IPv6 and there's so many, there's 128 bits, there is kind of a decimal notation sometimes people use, but you see hex a lot more compact. Okay, any questions? All right, so a subnet, by the way, is what you might have in your house, typically. And usually it's private addresses. I'll mention what those are in a moment, but very commonly you'll have /24 networks in your house if you buy a cheap router at some place that I won't say so many times because I'll sound like a commercial. Okay. Radio Shack. Okay, so today we're going to talk about routing some more and a little bit about DNS, and then maybe a little more about routing, and then we'll actually talk about TCP/IP. So IPv4, whoops. Dun, 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 dun. So IPv4 was actually divided up before the notion that addresses might run out, and it was divided up into a set of classes, and so there's class A, B, C, so on. So class A is something where the first octet is in the range 1 to 126, okay, and then the last 24 bits are not specified, and so we would call this a something .0.0.0/8 address, okay, because the subnet piece here is only 8 bits worth and the rest of the bits are free. These guys were actually handed out to some of the original folks on the internet, okay? So MIT, for instance, has 18 in this first spot. Okay, now the problem with that is, as you can see, if you hand out addresses this way, you use up big chunks of the address space really quickly. So, I can tell you for a fact that MIT does not have 2 to the 24th machines on their campus. They have a lot, but they do not have that many. Okay? Now, what's more common is sort of class B, where there's the first 16 bits are fixed, and class C, where, say, the first 24 bits are fixed. And if you look very closely here, you'll see that there's actually some funny subranges. Okay? So class B is really the first 16 bits, but notice that we have a 1 in the upper bit here, right? And why is that? Well, because when we don't have a 1 in the upper bit, we're a class A address. Okay, so you could kind of think of this as almost a Huffman coding. Okay, and then C and so on goes down. And these are basically the way addresses were handed out to organizations until people started realizing they're running out of addresses. Okay, and things got a little messier from there. And so a class B address might be something that a service provider acquires somehow, but then they'll hand out sub-pieces of their space and so on. And so it gets messy pretty rapidly. There's also some private ranges here, and I just wanted to point out a few key ones here. So for instance, in the class A space, if you have a 10 at the beginning, dot, whatever, these are private. Okay, so 10.xx.y.zz are private addresses. They're not routable. So if you put one of those addresses on the internet in the wild, it would probably get squelched very rapidly. It wouldn't go very far. And what are they intended for? Well, they're intended for organizations to have internal class A networks. Okay, so you could be a company and you could have, remember we talked about network address translation last time, you could have your own Class A internal network, 10 dot whatever could be what your machines are called, and then when they get to the public internet, they get routed and translated into a smaller number of valid ones on the outside. Okay? The other common thing here is 192.168 down here in the Class C. Anybody run into that address before? Right? So yeah, you basically, you got a home firewall you're configuring, you're likely dealing with the 192.168 addresses. It's just the way it is, okay? And that's private addresses. So if you tried to route these out in the public internet, they wouldn't go anywhere either. Yeah?
So since there's 254 IP addresses, what are the two other IP?
So the other two, when you have all ones in the subnet piece, or not the subnet piece, but the host piece, that's typically broadcast. Okay, and all zeros is usually an invalid address. It's just not used. Okay. Question, yes?
For the 127, or Class A 127, what is the loopback?
Oh, so loopback is basically when I send messages to myself. So when we start talking about sockets, you're going to see that the socket interface is sort of this nice abstraction, and it's really about there being two endpoints that you connect together, and then you communicate by sending in one side and you get a receive in the other. Whether those two endpoints are on the same machine or not is dependent on circumstances. Okay, so suppose they're on the same machine, so you effectively are communicating using sockets, but it's going out and coming back. That would go through the loopback address. Now, you might say that you're really sending to the IP address of your local machine, but it turns out that oftentimes that gets optimized to be this 127 dot whatever, usually 0.0.1, and that actually is an address that represents going back to where you come from. Yes?
So why are there 16 million loopbacks?
Yeah. You know, back in the day when it didn't look like we're going to run out of addresses, who cares? Okay? That's the best I can say. You know, in retrospect, a lot of things look silly from a historical standpoint, but this is just the way it is. So, any other questions? Yeah? No? Okay. So, by the way, in principle, with this Huffman coding idea where you add ones in places that are really class D, E, F, G subnets, but they get very small and people don't use them too often. So, how do we build up the internet out of this? Well, we've got a bunch of things, you know, locally and remotely in Europe and China and Asia and Africa. The question is sort of how do we build this network? And clearly there's hierarchy involved. There's no way that we are going to be able to make a connection, except on very specialized circumstances, say between here and somewhere in China directly. Okay, now there may be a few specialized connections using satellites, but by and large, what we do is we route things just like regular post office routes things, which you route locally, and then you route further and further and further, and then you route locally. It's all about hierarchy. And so, you know, you route within a subnet, and then you kind of, the subnet, you kind of route out to a router, and then maybe through a couple of routers or over a transcontinental link, and eventually you get through enough routers and you find the right subnet and you hit your destination. Okay? So routing is often by prefix. So just as I mentioned that the way we define the destination subnet is some number of bits are matching at the head, what actually happens as we go from source to destination is we kind of successively get more and more bits that match until we're in the final subnet where all of the subnet bits match. And then it's kind of up to the local infrastructure with switches and what have you to actually find the thing that's on your subnet. Okay? Yes?
Due to the hierarchical structure, you can't really bring your IP address with you. You move from the West Coast to the East Coast. There's not really much you can do. Is there a way to fix that?
So can you bring your IP address with you? Well, that let me give you an analogy. Can you bring your phone number with you? Well, today you can pretty much, right? And that's because they've sort of scrambled this full hierarchy of phone numbers, and there's kind of much more centralized routing going on. you could in principle do that, but right now it's much harder to transport your IP address from one place to another because they tend to have regions. But they're not defined regions in clean ways. So the fact you might actually have two subnets that look like they're next to each other sequentially that might be vastly separated. So it has nothing to do with the sequential numbering of the subnets, but rather kind of the way the hierarchy was put together and how things were handed out. But yeah, I would say in general it's hard to just transport your IP address. The one instance where that's not quite true, of course, is with a VPN, where what you're doing there, though, is you're actually kind of saying, well, I have my IP address, but I'm going to route through a third party and back again. And so the lowest level is kind of routing out and back, but they're giving you the illusion of a subnet with a separate IP address. So, yeah, question.
Does it sound like companies like Google or something can say, when you log onto their site, like, oh, the weather in Berkeley is this. They look at your IP and just assume.
Yeah, looking at your IP address is certainly part of what goes on. Yeah. And realize with Google, for instance, Google isn't one place, right? Google is everywhere. So when you make a Google query, you actually get routed to a pseudo-local Google set of machines, actually. Okay. So some simple terminology, which you've probably all heard. So what's a local area network? Basically small geographical area. So this might be a bus or a ring or a star network. We would say we have our local area network here in the building, certainly. You could also talk about that within Berkeley. It's probably in the 10 megabits to gigabit or 10 gigabits now. I probably should update this. Fast. In bit rate, it's also very fast to broadcast. I can easily send a message in a local area network that goes to everybody. Why? Because there's a lot of connectivity locally. Okay? And a wide area network is more of a geographical link. And these are basically where the hierarchy becomes very obvious, because you're basically going through narrow bottlenecks, which are point-to-point links, much slower. So for instance, you might get in the 1.5 to 45 megabit per second range, depending on what's going on. If you've got optical, this might be higher. The problem with broadcast is it's probably multiple messages, because it's not like you can broadcast to the United States. Okay, if you did that, you're likely to use up a lot of bandwidth and get a lot of people very pissed off at you. Okay, and that's just not a capability that's usually built in. Okay, and if you think about how would you broadcast to everybody here, is you'd have to send a message that then gets sent to everybody in the subnet. That's easy, but you'd also send a message that goes to every router, and then it sends the message to every router, which sends a message to every router, which then eventually sends it to every subnet. That's an operation you want to deny, right, normally, unless it's really for good use. And part of that sort of wanting to not allow broadcast in general, because it uses up a lot of bandwidth, is kind of why multicast, which is actually built into the IP spec, hasn't really gotten the play it's supposed to, because you're supposed to be able to send to multiple destinations easily in IP, and it just doesn't work very well yet. Okay, so there's also metropolitan area network, MAN. Anybody ever heard of that one? So yeah, so a lot of cities are putting in optical to everybody in the city, or they're having a I guess this is being applied to the wireless infrastructures that people are putting in. So you might say that San Francisco kind of has a metropolitan area network. But okay. So what about routing? So routing is the process of forwarding packets hop by hop through the routers to their destination. That seems easy, but you need a lot more than just the destination. You need a path. How do you get there, right? And it's the post office analogy, right? If I send a letter to Florida, it's not like somebody picks up my letter, hops on an airplane to Florida, or maybe gets in a car and drives for a really long time and takes it to the destination, right? It just doesn't happen that way. What happens is it routes to the local post office, which gets sorted. Maybe it goes to somewhere in the state of California, actually, and then from there it goes to Florida, and then from Florida it gets distributed to local places, and then the local postman carries it, right? So that's, again, very hierarchical, just like what we're talking about with IP. So when you're talking to a website, it really is the case that your packets are getting forwarded through this hierarchy to the server and then forwarded back. Okay, packet by packet. And it's very easy to forget. It's pretty seamless today to go, you go to a website that's in China for the Olympics, recently, and yeah, it just works. There's actually a lot of interesting stuff that goes on to try to get those packets there and back securely. Okay? And so the internet routing mechanism is actually a series of routing tables, and each router does a table lookup to decide which link to use to get your packet closer to the destination. That's the essential idea. It doesn't really necessarily know from every router where every destination is, but just which is the next hop that gets you closer. Okay, so you don't need 4 billion entries in the table because routing is subnet by subnet. The other thing that you may not have known unless somebody pointed out to you is that since there are so many routing tables, they can get inconsistent, and it's possible for packets to get stuck in loops. Okay, you send that packet off and it goes around many times and then dies. Okay? That would be an example of the internet being temporarily broken. And this actually happens rather frequently, okay, relatively speaking. And the reason it happens is that the only way you can get these routing tables is to run a dynamic algorithm that figures out the routing tables, and it doesn't always work correctly. Fortunately, it mostly corrects itself. Mostly. Okay? So what does a routing table contain? It basically contains destination, access, range to output link. So it's sort of, well, here's my packet. Let's see what is the closest I can get to the destination from the standpoint of matching my prefix bits. And so the output port that matches the most bits may be the one I go down. Okay? Now this gets a little more tricky because there's actually lots of domains that things route across. And so it may be that your packet doesn't route the closest way, but routes a way that your service provider has negotiated for packets of that class. And that gets a little more complicated. Yes? Yes? Well, so the question is, I said that it could get stuck in a loop. If you send it again, will it figure it out? So I wouldn't say that the packet figures it out, but rather the loop in the routing table may have repaired by then. But, well, there actually are some routing mechanisms that will choose different paths dependent on load. And so if you have adaptive routing going on, it might actually take a different path. Okay, so you can actually have more than one path to get to a destination. Yes? No, it's actually, I'll mention it it's much simpler than that. There's something called a time to live field that's in the header, and every time you hop, it decreases, and when you've expired your time to live, the packet goes poof. I don't think that it necessarily uses that optimization, but it's just basically running a protocol that's continually trying to converge, and so it will repair itself. But sometimes there can be holes in the internet for times that are visible to people. It happens. There's actually a rather famous case about a decade ago where there was a very important link in the internet that went through a tunnel in Baltimore. And there was some, I don't remember the story, I think there was some truck with flammable materials that went in and blew up in the Baltimore tunnel, and it basically partitioned the internet in two. Okay, because there wasn't enough redundancy. The infamous Baltimore tunnel fire. So suffice it to say that they try to make sure there are more than one path to get over major arteries these days. But there have been times in the past where that wasn't true. Yeah?
So default entry is like an output, a default output link, but it just sends anything that it doesn't have an entry for?
Oh, that's a good question. So locally, how many people have ever tried to explore their routing tables on their machine? Right? You can do that, right? And you look, and oftentimes you see a default entry. And what the default entry is something that's not really used in the core of the internet, but it is used certainly in client machines and even sort of in local parts of the local area network, which basically says, if I don't know how to get this packet somewhere, send it out the default link. And the notion is that you configure your default link to point at a router that's a little more knowledgeable. And oftentimes, by the way, that default route is part of the negotiation of DHCP. When you get your address automatically, it will give you a default. Yes?
So if routers in the core of the internet don't have default routes, does that mean they can only route a certain set of traffic then, or a certain set of addresses?
You know, I would say it differently. I would say if they don't have default routes, they're much more flexible to choose any of a number of places they could go.
But they could possibly not have an entry for an address.
They could possibly not have an entry, in which case they would drop the packet. If they really literally don't know where to go with something, they would just poof, it's gone. And that would be a hole in the internet that needs to be fixed by somebody. Yes?
Why is the default route necessary?
So the default, let's talk about the default route, because it's a good, it sounds like it's generating interest. Take a machine here at the edge. Okay, so this machine doesn't want to know much about the rest of the world, okay, because it's a small machine, it's managed by you, and you really don't want to be running a lot of dynamic protocols that are interacting with big chunks of the internet. So what happens instead is there are things you can get to on your subnet very easily, or a small number of subnets you're connected to, just because that's the way it was configured. I know I'm connected to this subnet, everybody on the subnet I can talk to. The default is basically a way to say, well, I don't want to have to know anything else, but if I don't know how to get something somewhere, I'll send it to this router here, which is really tied in with the rest of the protocol, and we'll know where to go. So it's really a simple mechanism to avoid having to run the kind of dynamic protocols like BGP, which I'll mention in a moment, that sort of figure out what the addresses are in the rest of the net. It allows a client to not have to run that stuff.
Why would the client have to behave any differently than just another router on that subnet?
Because an actual router is typically running a dynamic protocol all the time to figure out where the best way to send packets are.
Doesn't seem like that protocol would be all that expensive, though, would it?
It actually is. It's actually, and the interesting thing about BGP, the protocol running in the core of the internet, is it's so complex that there have been many papers written about how to optimize it, and many papers written about how it occasionally gets these anomalies where holes appear in the middle of the net. I mean, it's just do a Google on it, and I'll point it out in a moment. BGP for the Border Gateway Protocol. It's actually one of the things that people always say is broken about the internet, although it works most of the time pretty well. But anyway, so people don't really want to run it on their clients, and so that's where the default comes in. Okay. You know, it's also the fact that the router is always, I mean, think of my laptop, right? I opened it up here. I don't want to have to establish a protocol before I can route to anybody. Instead, I just want to get a default quickly to talk to a router, which has always been online. So that's another way to look at this. Okay. So questions on routing? Okay, so we've been talking about this already, but how do we set up the routing tables? Well, clearly the internet has no centralized state. No single machine knows the entire topology. And in fact, the topology is constantly changing. So you need a dynamic algorithm to basically figure out what the routing tables are. And ideally, every router would have an entry per subnet. But in fact, as long as it's got something that can basically get you closer to the address, you're good to go. So just to give you a flavor of possible algorithms, so this is one you'd never run in the internet as a whole, but you could run it in a building. There's various ones like OSPF is an example of this, where what you do is you flood the local network with packets that kind of say, well, here I am, and I'm going to say, everybody I'm one hop away from, you can get to me in one hop down the port you received this. And then they forward it on saying, well, you can get to that person in 2 hops and 3 hops and so on. And this is kind of an n-squared flooding algorithm. And what it allows you to do pretty quickly in a place like, you know, a building or maybe Berkeley is you can figure out routes that are direct with sort of direct cost, because you're sort of computing the cost as part of this algorithm. And so therefore, when you're done, you can say, well, I need to route to somebody. What's the smallest number of hop entry in my routing table that will get me there? And then you can effectively route directly there. Yes? No, because it kind of figures that out as part of the process. Because it's basically relying on kind of sending to everybody, which you can see is not a very scalable operation. So this obviously isn't used as a whole. In reality, the core of the internet has lots of different scales to it. So there's protocols that have to run. And this thing I mentioned, the Border Gateway Protocol, is an example of a protocol that's dynamically trying to figure out routes through the network. And it's not based, by the way, all the time on distance. It's quite possible that when you send a message from here to Japan, it actually routes in weird directions. Okay? And that's because oftentimes the reason that BGP will pick a route has as much to do with negotiation between different internet domains and what type of traffic is supposed to go through these domains as it does about distance. And the only way for BGP to really know truly about distance would be for it to run something like the n-squared algorithm I mentioned earlier, and it just doesn't. It's too expensive. Yeah?
Would these negotiations about the type of traffic be exchanged between internet domains violate net neutrality?
Would they violate net neutrality? Let's just say that there are no ISPs in isolation and they negotiate where their traffic goes. Whether it would violate net neutrality is hard to say. I don't think I've ever thought that all the way through. I mean, I think net neutrality starts getting violated when you give vastly different service to different people for no particularly good reason. But anyway, I think that's a whole discussion over beer or something, I think. Nobody, let me put it this way. Nobody has ever brought up the way BGP works as an example of violating net neutrality. How's that for a politic answer? Okay, so let's talk a little bit about naming now. So we've got these 32-bit addresses, which, it's great to remember what your address is, but it's hard, right? It's certainly the case if I want to look up a website, I don't want to do it by IP address. So it's really a question, again, of naming. We brought this up when we talked about files. How do you map human-readable names to IP addresses? What's www.berkeley.edu? Well, it turns out, as you all are aware, it's 128.32.139.48. And if you didn't know this by now, however long you've been at Berkeley, then clearly you haven't been on top of things. But I'm kidding, of course. And the thing about Google, if you didn't know that, www.google.com actually is a different IP address depending on where you go. Okay, if you do this at home versus in the office, you'll actually get different, or at Berkeley here, you'll get different addresses. Or if you do this on the East Coast, you'll get different addresses. Sometimes these different addresses have to do with locality, as I mentioned earlier. Sometimes they have to do with load balancing. So it could be that one address is to a machine that's way overloaded, and you might get a different address. Okay, so in fact, humans really want to deal with names anyway, so the fact that a particular destination name, which is a 32-bit integer or a 128-bit integer, is a useful thing to get there, really shouldn't be the thing you have to remember, okay? All right. And, it's kind of like remembering people's actual addresses is hard, too. That's what we have address books for. So why is this necessary? Well, IP addresses are hard to remember. IP addresses change, etc. Okay? So the mechanism for naming, we mentioned in the file system, was directories, right? And you traverse the directory. In the IP system, it's called the domain name system, DNS. Okay? And what is DNS? Well, DNS is, not surprisingly, a hierarchical system for turning names into IP addresses. And what's interesting about this is that basically, when you look for a say edu, suppose you want to go to mit.edu or berkeley.edu address, say we want to do this one, which is www.berkeley.edu, what happens is we start at the top level and we say to the top level of the DNS system, which are a set of servers that are actually managed by a somewhat global organization, we say, gee, how do I get to www.berkeley.edu? And it says, well, I don't know, but I can get you to berkeley.edu. Okay, and then there's a set of servers that handle berkeley.edu, and they say, well, I know how to get you to www.berkeley.edu. Go down here and look up in this name server, which handles this particular www.berkeley.edu, and that will give you the address. And so DNS is actually a series of queries starting at the top level, working its way through. Okay? And notice that the hierarchy here is actually a hierarchy in the dots in the name. So www.berkeley.edu is really resolved.edu.berkeley.www. Okay? And that hierarchy has absolutely nothing to do with the IP hierarchy I mentioned earlier, which is sort of subnets and so on. Okay? It's completely different. And, okay, is everybody with me on that? Now, of course, if you got something that's that expensive, ask this, then ask this, then ask this, then ask this, then ask this. What do you do to make it faster? Caches. Oh, we got you guys trained now, right? So DNS has as a fundamental aspect caching. Okay, and of course, caching has to be kept coherent with the world as a whole, and that's tricky. And in fact, you don't actually try to keep it fully coherent. What happens instead is your entries that are cached for DNS are allowed to expire after a period of time, and that period of time is often something like 24 hours. Okay, I don't know if anybody, probably not so much, but if anybody here has ever had a name that had one IP address and they changed it to another and then they started looking at it over and over again and nothing happened. Okay, and that's because your name is cached. Okay. Now, how important is it to have DNS work properly? Very. Good answer, right? So if an attacker manages to make the address mapping incorrect, they can do all sorts of stuff, right? They can get someone to route to their server thinking that they're going to their bank. Now, of course, with something like the web, we have SSL and certificates which try to prevent that from happening. But in general, you can imagine that if you can get routed to an arbitrary server instead of the real server, there's a problem there. Okay, and you might then ask this question, which is a perfectly reasonable one that not enough people ask: is DNS secure? Okay, well, it's definitely the weak link in a lot of IP things. Okay, and if you manage to query DNS and it were to give you a response that was bogus, then you could screw up IP. Okay, and in order to avoid substitution attacks of this sort, every DNS query actually has a random number in it so that only the person that got the original query returns the right random number, then you're good to go. Okay, and you can sort of assume that maybe the wrong person hasn't been sending your response. How big is this random number? No, 16 bits, which is not very big. Okay, and actually in July of 2008, you probably didn't notice this, but there was a rather interesting scenario where all of a sudden everybody was told they had to repair their DNS servers, and they weren't told why. And the reason was that there was actually a hole discovered in, or actually an attack, I would say, discovered in DNS, which basically figured out how in a given ISP, if you could get one user to go to a bogus web page that did enough queries, that there could be a guessing attack against the 16-bit ID, and as a result, you could cause the cache of the ISP to get a bogus root server installed for a certain domain, and then it would be giving bogus addresses to everybody in that ISP. Yes?
Doesn't that make it so you have to randomize your source ports, though, which is 16 bits?
Yeah. So the sort, basically, one of the ways that they, well, the first thing they did was they basically had to they made it much harder to do this, and one of the things they did is they randomized the ports. It turned out it was originally the case that all DNS queries from a given client were always on the same ports, and they basically randomized that to make it more complicated. Yes? Yes?
Is the DNS lookup handled by the operating system or application?
It's actually typically handled by, well, depends on what you call operating system or not, but there's often a DNS server that you query, and the server handles it, but that's a local server, and it talks to remote servers. So it's a service that's running oftentimes. Okay, so DNS needs to be secure, and it wasn't. And this was actually an interesting sort of well, you better all fix it, but we're not going to tell you why. And they had to get everything fixed before anybody was told why, because this was a pretty serious hole. I think Kaminsky here was able to break into things in like 8 minutes or something. Go ahead.
What is there to stop somebody from setting up like a rogue DNS server, just saying that they knew where to forward everything to?
That's a good question. So what is it, what would prevent somebody from setting up a rogue.edu server? And the real answer is because the queries are top-down, you've got explicit things you're forwarded. Like when you query the top level and you say, I want the .edu server, it gives you a good server. And so because nobody will forward your address of your bogus server for a domain you're not actually supposed to have, and that's basically the simple answer. Now, you could imagine fooling the .edu server into putting an entry for Berkeley that was something other than Berkeley, but that's now a problem with the administrators of this machine. So the real problem is that at the face of it, it looks like you couldn't do what they did with DNS because it seems like you'd have to somehow fool the servers into giving out your bogus DNS server. And what actually turned out, it's DNS. When you return information with DNS, it turns out you can return a lot of things other than what was asked for. And so what they would do is they would figure out how to, once you made a query, I would send you an answer before the real answer came by, and I'd put a bunch of information you didn't ask for, but you might blithely cache as being valid. And as long as that 16-bit ID matched, I would fool you into saying, oh, here's a real response from that server that hasn't actually responded yet. And that was where this hole got into play. It was a timing bug. Okay. Good. So, Administrivia. I know. Final exam coming up. It's actually in 10 Evans. And you need a dumb calculator to do calculations, but no cell phones, no devices with networks. If your calculator looks like it's might talk back at the TAs, it probably won't be allowed. So find yourself a little four-banger scientific something or other. And I'm giving you several weeks to do so. So I'm sure I know it's old school, but I'm sure you can find one somewhere. There is a lecture next Wednesday. Believe it or not, we'll probably be talking about distributed file systems. Hopefully the web will be up, but we actually lost somehow the last 26 minutes of lecture last Monday. So I don't know. Hopefully it'll be there. And then, of course, final lecture. I've now gotten officially 2 people sent me stuff. I have one of them was actually I haven't fully read them yet, but I've got them. I know I have 2, and I know there was stuff in them, so that's good. But I need more. So send me more, and I will actually summarize what I've gotten when I have more than 2. So please send me more things to query. Okay. All right, yeah, real-time secure quantum dragons, yes. Okay. Any questions on Administrivia? No? Okay. Yeah, actually, so one of them recently was all the interesting distributed systems that are out there today. And there was another one that was a couple of days ago. But anyway, I will look at them very carefully, obviously, when I'm putting a lecture together. So, okay. So, performance considerations. So let's now talk a little bit more about some things that we might want to get out of our network. So let's get some performance metrics. So overhead. Okay, this is typically used to refer to the time to put the packet on the wire. Okay. Throughput is the maximum number of bytes per second that we can send. Now, clearly, this depends on wire speed. Okay, that goes without saying. So if you've got a 1 gigahertz link versus a 10 megahertz link, that's going to be different. It's also limited by the slowest router. So if you've got a router in your path that's incredibly slow, it takes a packet in, it looks at it, it computes a few digits of pi, and then it sends it on. Obviously, your throughput's going to be lower for a connection that goes through that router. Okay? Latency is the time until the first bit of the packet arrives. So when I start sending a packet to some destination, when the first bit arrives at the other side, that would be the latency of that connection. Okay, and so it's kind of raw transfer time plus overhead at each routing hop. Now, what are the contributions to latency? Well, you can see if I send a packet from point A to point B, I've clearly got the latency on the wire. I've got the latency in the first router. I've got the latency on the second wire, the latency in the second router, and the latency on the third wire. These are all components that need to be added together to get the total latency. Okay? Now, wire latency actually depends on speed of light in the wire. Okay, does anybody know what the speed of the light in the wire, or why do I say it's 1 to 1.5 nanoseconds per foot? I will say that that's slower than the real speed of light. Yes?
Oh, like light travel, like so say you're using fiber optics, light travels slow. It's like roughly 2/3 the speed of light.
Yeah, exactly. So the speed of light's actually slower than the speed of light in most things you're likely to encounter, unless you're actually sending light through free space. Okay, so in particular on a wire, and an actual wire, this is a good number to remember. It's about 1 to 1.5 nanoseconds per foot for a wire. Okay? And of course, the router latency depends on the internals of the router. Good routers are probably less than about a millisecond. Okay? Bad routers could be more. Anybody know what the ping time is to a server in the building here? Anybody try that? Round trip?
Like 6 milliseconds.
Yeah, it's order 1 to 10 milliseconds, probably 1 millisecond if it's good and not if it's bad. Good. So some sample computations. Let's go through these and then we'll take a break. So Ethernet within SOTA. So the latency, speed of light in the wire is about 1.5 nanoseconds per foot, which implies that the latency to go across the building is about a microsecond if there's no routers. Okay, so clearly wire latency not a big issue inside of SOTA. Okay. Throughput, yeah, we're getting up in the gigabit links everywhere pretty much. Okay, so we still probably have some 10 megabit, no, I doubt we do, 100 megabit links maybe. Throughput delay, so the packet obviously doesn't arrive until all the bits are there. So if we have 4 kilobytes in a packet, 100 megabits per second, that's about 0.3 milliseconds. Okay, if it's 10 times, or if it's a bigger packet, obviously this goes up. If it's a faster rate, this goes down. But this number here of order 1 millisecond is about the order of a disk. Okay, which is kind of interesting because people did talk about rather than going, or it's actually slightly faster than the disk, rather than going to disk, why don't we go talk to memory on a different computer, right? So that was an actual comparison that people did once. What about ATM within SOTA? Now ATM is I mentioned before the asynchronous transfer mode protocol that was used, one of the first packet switch networks that was used cross-country. It's used for phones. The latency is the same, because it's over a wire. Throughput is more like 155 megabits per second. Throughput delay about 200 microseconds versus the 300 microseconds up here. Okay, so that's slightly, and that's because we've got a slightly faster connection. How about cross-country? Okay, this is when things get interesting. So the latency, assuming no routing, is about 3,000 miles times about 5,000 feet per mile, right? That's rounding it off. About 15 milliseconds. Okay, and I'm basically computing a nanosecond per foot there. How many bits could be in transit at the same time? So this is the first time we have a slightly different number here. So at 15 milliseconds times 155 megabits per second says there could be about 290 kilobytes of data in a long packet that's stretched all the way across country using ATM. So imagine that I just start transmitting and the bits are just spreading out, and by the time the first bit arrives, I will have put 290 kilobytes into the link. Okay, now why is, yeah, go ahead. Yeah, you need routers in the middle there, but okay, so, yes, but hold on to that question for a second. So what the routers are going to do, by the way, what the routers are going to do is they're going to increase this time, and so the total amount of data that I will have sent before the first byte shows up is longer. Now the question is, why am I even bothering to compute this number? I mean, this probably looks bizarre. 3,000 miles times 5,000 feet per mile, 15 milliseconds. Why do I bother computing that number? Why is that interesting? Yes? Okay, what about the best case scenario? Okay, but what? Okay, good. I'll buy that. But then why am I multiplying by the bit rate to compute a number of bytes? Yes. Yeah, so if I want this link to not be wasted somehow, I want to make sure that I have at least this much in transit so that none of the links in the pipe are idle. Okay, because if I just send a little tiny packet off and it works its way all the way down, I've got all this wasted bandwidth in the middle and I'm not really using my link well. Okay, and so when we start talking about how to get good performance out of, say, TCP/IP, we're going to wonder a bit about this number. How many bits do we want in the link? And in fact, for instance, the Berkeley to MIT latency is about 45 milliseconds, not 15, and that's because of the routers. Okay, and so that basically, if we add that up, we say we've got about 872 kilobytes in flight at time. Okay, while we are going from Berkeley to MIT. Okay, so to finish this off, the requirements for good performance in the local area. We really want to minimize our overhead and improve the bandwidth as much as possible because we've got short links and we're trying to just make best use of the network. In the wide area, we want to keep this pipeline full so we're not wasting any links. Okay, so it's going to be kind of a different requirement for the local and the wide area. All right? Good. So let's take a break. Come back in about 3 minutes or 4 minutes. All right. So, Let's switch gears a little for the rest of the lecture and talk about protocols now. So a protocol, as I mentioned last time, is an agreement between two parties on how information is transmitted. Okay? And an example, you could say that system calls are a protocol between the operating system and applications. Okay? Maybe that's a stretch. Networking example have many levels, and that's where they come up mostly. And I'm not actually going to go through the full, OSI stack. That would be 122 for you, but I want to actually, you take 122, but I actually want to give you some flavor for why the levels are there. So at one point is the physical level, and this is things like mechanical and electrical network issues, like how are ones and zeros represented? How are they transmitted? How do they get to the other side? The link level has to do typically with what's the format of a packet on the link and what's error control. An example, for instance, CSMA-CD, which we mentioned from Ethernet. This was the carrier sense multiple access carrier detect protocol. This is the link level, which is basically making sure that a packet makes it to the other side. Finally, at the network level, we start worrying about things like network routing and addressing. Okay, so IP is a network level protocol, and so that's why routing is typically an IP thing in an IP network. Okay, and this is, if you think of these as physical and link as 0 and 1, network is typically level 2, and so most routers that are not very intelligent are considered level 2 routers. And then once you get above network level, there's transport level, and this is all about, well, I can get packets to the other side, but I don't know what order they're in, and I don't know whether they actually make it or not. And so that's where we put reliability in, and of course TCP/IP is a good example of a transport level protocol. Okay, so there's all these different levels, and here's just, the physical and link level is where we've got things that we typically associate with actual types of networks, Ethernet, ATM, packet radio, 802.11 wireless, those kind of things. 4G if you're Sprint, or I guess now, who else? There's a couple. Verizon, yeah. So what your physical layer is, of course, should not matter if you're routing IP on top of it. So IP gets put on top of these physical links, and that's how you get this ability to send a packet from here to China. It doesn't matter whether the server is going over Ethernet or ATM or something else, because the IP protocol has been properly put on top of all of the different links in the system. Okay, and that's why this layering is so useful. The transport level is then on top of IP, and that's where we get, for instance, TCP for getting reliability, or UDP for getting fairly fast datagrams. So that's the transport level. And then above this is kind of all the uses. Okay, and that's where we get remote procedure calls to get NFS and World Wide Web, or maybe directly on top of TCP and email and SSH. All of these things are users of the transport protocol. So you'd have to take 122 to really go into a lot of detail on this. And how many people said they were in 122 this term? A couple of you. How many people have taken 122? What was it? Oh, what? Oh, it's on top of this class. Literally on top of this class. Okay. Oh, it's above this class too? Okay. So obviously we can't cover all of 122, but we're going to cover enough here to get a little flavor. So layering is basically building complex services from simpler ones, and you saw this clear layering here, building transport on top of the network, building the network on top of the physical layer. That's layering. And each layer provides the services needed by the lower layer. And so the physical link layer is pretty limited. Okay, so packets are of limited size, and this is often called the maximum transfer unit, MTU. That's a good thing to remember. Sometimes that shows up in exams. It's often in the 200 to 1500 byte range. Okay, so for instance, in a typical IP network, you often won't see something bigger than 1500 bytes, but if you happen to send packets through a lower performing router or network, the MTU can get as small as 200 bytes. Okay, and what this is this is the biggest packet that you're allowed to shove on that wire before it gives up and throws it out. Go ahead.
Why would you want to have such a small maximum unit? Why would you allow
So the maximum transport unit here, transfer unit, excuse me, has a lot to do with the technology you're using. So a great example is ATM. Okay, has a 53-byte packet size. Okay, now why is that? Well, it turned out that that was basically picked because that was kind of the maximum size that didn't have echoes transcontinentally in certain circumstances. So it can depend a lot on the technology. When the technology doesn't limit it, 1,500 bytes was kind of a limit that was really required when you had kind of the more traditional cables in the ceiling and so on to avoid reflections. With today's modern point-to-point Ethernet configurations, 1,500 bytes is kind of an anomaly, or excuse me, an anachronism. That was the word I was looking for. It's basically something there historically. Most things use 1,500 MTU, but it turns out if you have your own network, you can get what are called super packets, and you can get 9,000 byte MTU because it's fine to handle that on Ethernet. So some cases, this number is historical. You'd like to make this number as big as you can, but if you make it too big, then sometimes you start running into problems when you go through gateways. And so usually the bigger than 1,500 MTU only shows up on a subnet. Question, yes? Okay. But the key thing to get from this small number is not, where it comes from is very interesting, but also the fact that it exists means we got a problem if we want big packets or big things. A web page is not 200 bytes. Question, yes? So a smaller size might either allow greater success per packet, or it may be something physical. It may have something to do with the queue sizes. There could be lots of reasons why you have a smaller size. Best way to think of it is a physical limitation. And each individual one, you'd have to read about why it's there. So our goal is basically to take these little tiny packets, which, by the way, are also unreliable. There's no guarantee when you send a packet along a link it even shows up at the other side. We want to try to turn this into an abstraction that's useful to us. So our physical reality might be that packets are limited size, they're unordered, which means that maybe they arrive out of a different order than you send them. They're unreliable, meaning they either don't show up at the other side or they show up and they're corrupted. The physical reality of the link level is it's only machine to machine. Remember, we started out this lecture with point to point. So at best, over the link, I can send a message to the machine I'm immediately connected to. Okay, a lot of good that does me, right, when I want to send this to Europe. So physical reality packets only on the local area network. That's kind of the same idea. Physical reality packets are synchronous, or asynchronous, So they sort of show up when they want to, and they're probably insecure. So we might want to actually have more, a better abstraction, like arbitrary size. They might be ordered, so data shows up in the same order I send it. It might be reliable. If I send data, it shows up. It might be from process to process, a process here, a process in Beijing communicating, not a machine here and the one I'm immediately connected to. Okay? We want to route them anywhere. We might want to make sure things are synchronous. In other words, we have some timing on things, and we might want to make sure they're secure. So I would say, at the risk of offending my networking colleagues, the whole point about networking is turning limited things into useful things, okay, where communication has something to do with it. Now, and of course, you want to make it fast, and and it gets very interesting as you go with that. But what we're going to do is we're going to talk a little bit about how to get some of these useful abstractions out of this limited piece, okay, and that'll be kind of the rest of our lecture here. So, how do we build a message service? Well, suppose we want to handle arbitrary size messages. What do? Well, we take the big messages, we split them into little messages. Okay, and somehow we reassemble them at the destination. So obviously this doesn't surprise anybody, but it seems like we've got to have at least some layer that does that for us, and this reassembly might get tricky if they're out of order. Okay, and possibly we want to compute a checksum on every fragment to make sure the fragment makes it to the other side. Okay. So IP is a protocol, as we mentioned. It basically finds a way to send packets to arbitrary destinations in the network. It delivers messages unreliable, best effort, okay? And so basically, this is kind of the abstract layer that is our limited packet layer. Unreliable intermediate links may have limited size, so even if we started out with an MTU of 1500, it may be that somebody in the middle demands an MTU of 200, and so something has to happen there. Okay? And the IP protocol, by the way, has 256 sub-protocols, okay, and they're numbered from 0 to 255, and so good examples that you're all familiar with is ICMP is 1. Does anybody know what ICMP is? Ping. Okay, and this is the Internet Control Message Protocol, ICMP. TCP, okay, that's what you get web pages with, or what you SSH into. What about UDP? Yes? DNS, okay, what else? Yeah. Videos, yeah, so this is a very low overhead, unordered datagram protocol. And then IPsec is basically a way of putting an encrypted secure channel on top of IP. Okay, and so these are sub-protocols, 1, 6, 17, 50, 51, so on. What's the format of an IP packet? I'm sure you all wanted to know. Well, there it is, all 20 bytes of it, okay? If you forget any portion of this, you're going to be in trouble. I'm kidding. Let me show you a little bit here. So there's a few bits that say that this is protocol 4. As far as I know, this is the only IP protocol where there's a 4 here. IPv6 packet format's a little different. There's a number of bits that say how long is the header, okay, which is 20 bytes. There's a type of service, which we won't talk about here. There's the total length, which is the size of the header plus all the data that's attached to it. And then a couple other things. Here's that time to live field. Remember I mentioned earlier that a packet could get stuck in a loop? Well, what happens is at every hop, the time to live field is decreased, and if it ever gets to 0, the packet's tossed out. Okay, so that's what this time to live field is for. Does anybody know the cooler thing other than sort of preventing loops that time to live is used for? Yes? Yeah, so what is that called? Yeah. Trace route. Yeah, the program's called trace route, or in Windows it's trace RT. And you give it a destination address, and it shows you every hop along the way. You should try this sometime. It's fun. It's kind of cool. The way that works is it starts with a time to live packet of 1, and it sends it to the destination. The thing goes 1 hop, it dies and sends back a I died message, and then it does a hop of 2, and it sends back an I died message. And so that's how it finds out what every hop is, because it keeps increasing the time to live field. Okay? This is 8 bits here, so the 8-bit time to live field. Here's 8 bits, which is a protocol. So if you've got ICMP, this 8 bits will be the number 1. If it's TCP, it'll be 6, and so on. So that's where the protocol is placed. Okay? And then, of course, there's a 32-bit source and destination IP address. Now notice the only thing here is a source and destination IP address. So IP is fundamentally machine to machine. There's no process to process aspect. Yes, question? No. Options is actually for other stuff. We'll get, when we wrap the TCP or UDP header on top, we'll get ports. There's a whole bunch of additional, you can make the IP header longer by putting options in. There's a bunch of them. They're not used very often, but they do exist. Okay, questions? Yes? So the checksum, once again, is a way of detecting packet failure by basically taking groups of bytes and just XORing them together, and if any of the bits get changed, then the checksum won't match at the other side. Yeah. And it turns out that IP has a very specific way of computing the checksum, which is sort of taking 32 bits at a time and rotating them at each sort of set of 4 and XORing them together, and then taking the results and XORing them. It's in the spec as to how you're supposed to do it. And I haven't looked at it in years. I implemented it once a long time ago, but it's been a while. But you can look it up. It's there. Okay, so how do we build a message service on top of IP? Well, we want process-to-process communication. So it's not the options. We'll show you in a moment. So basic as we said here, gets packets. The basic IP protocol goes from machine to machine. So in order to go from process to process, what do we need? Well, everybody says ports. We need something else, some other piece of information that identifies uniquely an endpoint in that machine, another process. Okay, and the idea here is what's called a port. And for the typical IP protocols like TCP and UDP, the port is a 16-bit number. Okay, and so what you can think of as a communication channel over either UDP or TCP IP is actually a 5-tuple of source address, source port, destination address, destination port protocol. And it's these 5 things that make a unique connection. Okay? And so that means, for instance, you can actually have UDP and TCP that have overlapping source address and ports because it's a different address space because of this part of the 5-tuple. Now, so UDP is the simplest example here of an IP protocol. And what it is there's the IP header, which is 20 bytes here. And if you were to look into those 20 bytes, you'd see where it says protocol here, it says 17. Okay? And then what's added here is an extra 2 32-bit words. And one of them has a 16-bit source and a 16-bit destination port, a length of the total packet, and then a checksum, which is independent of the previous checksum, and then the data. Okay, and this is what's called a datagram because when you send it, it's not guaranteed to get there. It's not guaranteed to be in any order. And it's sort of sent as a unit. Okay, but it's a process-to-process datagram that is unreliable. And that's what UDP is. Question? Yes?
It seems like we have enough protocol numbers to build new hardware stuff. We've only got 256 ones. So if we need to define a new hardware protocol, or a new protocol to use, like what do we do?
Well, they haven't run out yet. There's a lot of IP protocols, but I don't think all 256 of them are in use. I think the bottom line is, IPv4 is sort of long in the tooth for lots of reasons. What we really need is a new protocol like, say, IPv6. I don't know whatever happened to 5. But anyway, we need, yeah, the bits are running out. But actually, in terms of protocols, there aren't as many as you might think. Yeah?
So is UDP just basically IP between processes?
Yes. So you could think of UDP as IP between processes. I'd buy that. Now, what we were mentioning, the important thing about UDP is it's low overhead because there's not much more than packaging it off and tossing it at the destination and it shows up there. And so that's why UDP is used in cases where you want very low overhead like video. Or it is also used, you can put the network file system in a mode that uses UDP on local area networks if the loss rate isn't too high. You can put UDP is used for DNS and things like that. Okay, so it's basically a very low overhead protocol. I point out, however, that many uses of UDP are actually kind of considered antisocial. And the reason for that is you can send more UDP packets than anybody can receive along the destination or even in the routers in the middle. And as a result, you can overload them all. Okay, so you can actually send more UDP traffic than can make it. And that's because there's nothing in the UDP protocol that tries to suppress the amount of data being sent. Okay, there's nothing. Basically, the sender can just send as rapidly as possible. And so it's kind of up to the user of UDP to be social, and not everybody is. Now, fortunately, with a lot of firewalls and border gateways and so on actually track what's coming from where, and it will suppress traffic that's antisocial. So there's a lot of work done in the middle of the core to kind of get rid of antisocial traffic, but you can still be pretty antisocial with UDP. Now, let's talk a little bit about ordering. So UDP is like, that was a good analogy. It's IP between processes. So suppose we want to order messages now. So several network services you could imagine are something like do A, then B, then C. But if you send packets off and they arrive out of order, you could end up doing C, then A, then B or something. Okay, and so what do we have to do to order our messages? Got to count them or something, yeah, okay? And before we fix this, let me point out that I'm not actually making it up that things arrive out of order. The underlying network is packet-based, and therefore there is no ordering enforced. Okay, and the simplest way to see how a packet's going from A to B could be misordered is you send 2 packets off, and they get in the middle of the network, and one router holds on to them, one of them for a while, but lets the other one through. Well, that would be a simple way to imagine it. Or one of them gets dropped and retransmitted. Now we're out of order. Or there are 2 different paths that are taken in the internet, and they arrive out of order. Okay, so there's many reasons why packets going from source to destination aren't going to make it there in order. So this notion of needing to reorder them at the end is very real. And so what do? Well, we got to queue things and reorder them. I mean, basically, that's the bottom line. And the total amount of misordering there kind of impacts how much queue space I want. So if I've got gigabytes of data divided up in little 1 kilobyte packets, and they're completely misordered, I may need gigabytes of space at the destination to reorder them. Okay, now fortunately, although misordering happens, it's not that drastic usually. Okay. So how do we get ordered messages? Well, everybody said we add sequence numbers. Okay, first message has 0, second has 1, third one, okay? And if the packets arrive out of order, then we hold on to later packets until the earlier ones arrive, and then we hand them to the user of that process in order. Yes? Well, if the sequence numbers cycle, then we got problems. Okay, so we got to make sure the sequence numbers are monotonic, at least for this connection. Okay, or at least they don't have to be monotonic if they wrap, but at least they have to be not wrapping back on a short sequence. Yeah. So that's a great question. Hold on to that for a slide here. We'll talk about dropped packets. So sequence numbers are clearly specific to a particular connection. So you can reuse sequence numbers between connections. Okay, and you normally don't care about reordering about 2 different connections. Normally a connection is the thing that's ordered. And if you restart the connection, you need to make sure that if there happens to be old packets from the old connection floating around, you're in a different part of the sequence number space so that you don't confuse a delayed part of the old packet from a new packet. So let's talk about Let's talk about reliable messaging for a moment. So physical networks can garble things. So examples of physical media garbling things, if you transmit close to the maximum rate, you might get mostly really high bandwidth, but occasionally garble stuff, so it's easy to get garbling there. Or if you transmit at a fairly low voltage to try to save energy, you might get garbling there, and that's okay. If you have congestion in the middle of the network, the routers can drop things, so that's a form of garbling, namely the thing doesn't show up at all. Okay? And there's lots of places where congestion can come into play, like a point-to-point network. You might have an insufficient queue at the router, okay? Or a broadcast link. You have 2 hosts try to use the same link. Or insufficient buffer space. Or rate mismatch. The sender is sending faster than the receiver can receive. These are all reasons why you got to drop packets or do something else, okay? And that you could consider that a form of garbling. So how do we get reliable message delivery? What's the simplest way to get reliable message delivery? Yes? Yeah, acknowledge, exactly. So we need some way to make sure that packets actually make it. We need to make sure that each packet's received at least once, and each packet's received at most once. Okay? And the reason we want the at most once is because if each packet reception does something, we don't necessarily want to do it twice, because not everything's idempotent in that way. Okay? So, and we can combine this with ordering because we can acknowledge with sequence numbers. Okay, so here's an example of how to ensure transmission of packets. And the way to do that is packet sent to the destination, it acknowledges. Okay? However, what happens if the packet's lost? Well, at that point, we don't get an ACK. So what do? Well, we got to retransmit at that point. Okay? And so notice that the sender has actually got to hold on to every packet until it gets an ACK, because otherwise it may not be able to resend. So the sender is holding on to things, and the receiver is going to acknowledge as quickly as possible. Okay, in order to avoid the timeout at the source. Yes? What happens if an acknowledgement gets dropped? That's a good question. So what happens is we're going to treat a lost acknowledgement the same way as a lost packet, and we'll end up retransmitting. So what's interesting about that scenario is then you actually end up with 2 packets of the same thing, right? So if the sender doesn't get an ACK, does this mean the receiver didn't get the original message? No, that was the case you just came up with. It may be the sender did get the message. What if the ACK gets dropped or if the message gets delayed? Then we can get multiple transmissions. So for instance, suppose this packet goes from here to Stanford by way of New Hampshire. Okay. Meanwhile, the timeout happens and you resend. It's possible to get double packet reception as a result. Okay. So we will work on this next time. So in conclusion, we talked about DNS, which is the system for mapping from names to IP addresses. It's a hierarchical mapping from authoritative domains, and there are some flaws that have been discovered and patched in various ways. Talked about datagrams, which is a self-contained message whose arrival time and content are not guaranteed. And we talked about some performance metrics, namely overhead, throughput, latency, that are important. And we started talking about how to order messages using sequence numbers and how to use acknowledgments for reliable messages. And next time, we'll actually introduce TCP and talk about the internals of the TCP protocol. So you guys have a good weekend, I guess.